Hello, my name is Zach, and I'll be presenting the longitudinal autopilot design for the AERO4600 Assignment 3, completed by Group 7. Our project was a collaborative effort. Noah developed most of the code, Mitchell contributed to both the report and coding, Lewis helped with the report and presentation, and I prepared and edited the final slides. The aim was to design a practical nested longitudinal autopilot. The inner loop stabilizes pitch rate, the outer loop commands vertical speed, and a throttle loop regulates airspeed. All designs were based on the linearized aircraft model at 180 knots, ensuring realistic dynamic behavior. This type of autopilot reduces pilot workload and maintains smooth, accurate climbs and descents, especially in turbulence. Command limiting logic also protects the aircraft from actuator saturation during large inputs. Our first task was to determine whether the elevator alone could control vertical speed. We linearized the aircraft at 180 knots and analyzed the open loop transfer functions between elevator deflection and both vertical speed and pitch rate. The vertical speed transfer function contained an integrator, giving infinite DC gain. That means any constant elevator input would cause vertical speed to increase indefinitely. Meanwhile, the pitch rate transfer function had complex poles near 5 radians per second, the short period mode, showing it's better suited for control. The bode plot shows the negative 20 decibel per decade slope and negative 90 degree phase at low frequency, with a sharp resonance near 5 radians per second. The phase never recovers enough for a stable crossover, so direct elevator to vertical speed control would be unstable. The root locus confirms instability. The poles move toward the right-hand plane as the gain increases. This means we must first stabilize the short period mode using a pitch rate inner loop before adding a slower outer vertical speed loop. For question 2, we designed a pitch rate feedback controller. We targeted a 3-second settling time and a crossover near 5 radians per second, adding lead lag compensation to shape the loop. The tuned controller achieved a 5.8 radian per second bandwidth and a 3.3 second settling time. It provided stable, lightly damped behavior, ideal for the inner loop. This plot shows the open loop response with a smooth negative 20 decibel slope and a roll-off past 20 radians per second. It meets our noise attenuation and crossover targets. The pitch rate step response settles in about 3 seconds with roughly 40% overshoot, matching the assignment requirement. This plot shows the closed loop frequency response. The system tracks pitch rate commands accurately through the mid-frequency range and rolls off smoothly at higher frequencies, confirming the inner loop is stable and well tuned. With the pitch rate loop working, we added the outer vertical speed loop. It converts vertical speed error into a commanded pitch rate tracked by the inner loop. The outer loop achieved a rise time of 2.9 seconds, settling in 10 seconds with only 3% overshoot, smooth and accurate behavior. This diagram shows the nested structure. Vertical speed commands feed into CVS, producing QC for the inner loop. When commanded to climb 500 feet per minute, or around 2.5 meters per second, this plot shows the aircraft reach the target cleanly with minimal overshoot. During that vertical speed step, the pitch rate peaks early and decays within 3 seconds, showing effective short period damping and good loop separation. The elevator deflection stays small and smooth, only a few milliradians, demonstrating efficient actuator use. Here we introduce throttle control to form a 2-input, 2-output MIMO system, elevator for vertical speed and throttle for airspeed. Both compensators were tuned with the same 3 and 10 second targets. This diagram shows both channels and their crosslinks, representing aerodynamic coupling, meeting the full system modeling requirement. Both vertical speed and airspeed responses track commands accurately with well-coordinated control action. Cross-coupling is minimal. A step in one channel barely affects the other, confirming good decoupling performance. Elevator and throttle movements remain smooth and well within limits, confirming the MIMO autopilot is stable and practical. We then tested all controllers together in the full 6 degree of freedom nonlinear model to confirm the linear design held under realistic conditions. The nonlinear airspeed matches the linear design closely, with only minor offset due to drag and power effects. The vertical speed is also almost identical to the linear model, with smooth tracking at about a 7 meter per second climb rate. The pitch rate transient is well damped with no short period oscillation, and the inner loop remains robust, stabilizing the aircraft effectively. Elevator and throttle deflections stay smooth and within range, proving the full autopilot remains feasible in nonlinear flight. To test gust rejection, we used a Dryden model with 2 meter per second RMS turbulence. The RMS vertical speed deviation was 0.25 meters per second, with peaks under plus or minus 0.6 meters per second. Under this Dryden gust, the linear controller attenuates low frequency disturbances, keeping oscillations small and stable. The nonlinear model shows only slightly larger deviations, mainly from aerodynamic coupling and actuator limits, but overall stability and disturbance attenuation are maintained. This is consistent with real aircraft behavior during turbulence, confirming robustness. To protect against excessive commands, we applied plus or minus 7.6 meters per second vertical speed limits and 10 degree per second squared rate caps, preventing short period excitation. With limiters active, the climb command becomes smooth and stable, with no oscillation or saturation. Here we see the same limiter applied to the linear model. The response is consistent with the nonlinear case, being amplitude constrained, stable and well damped. This confirms that the limiter strategy generalizes across both models and provides reliable protection against excessive control action. To conclude, we proved direct elevated to vertical speed control is infeasible, built nested pitch rate and vertical speed loops, and integrated throttle to form a stable MIMO autopilot. The nonlinear tests, gust rejection, and command limiters all confirm stability, safety, and robustness. Overall, our design met every requirement of the assignment brief and therefore designed a complete and practical longitudinal autopilot.